worden, zeg maar, degene die online gaat volgen. Dus zullen we beginnen? Welcome everybody here in this room. I'm very happy to be here to defend my PhD in front of you as the audience. And despite the very difficult situation with respect to coronavirus and the restrictions that we have. That's my great pleasure to defend my PhD. And also I'm very happy to have the opportunity of online streaming, live streaming for the people who are following this presentation by the link that I have shared in LinkedIn. And I heard from people that they will be watching almost from every continent. So that's make it even more interesting. And also from this place, I would like also to thank everybody who is following online. Finally, I would like also to say welcome to my parents and my family members, except, of course, my wife who is sitting here, who are following online as well. And because they don't know English, I would say a few words in Persian. سلام به همگی. خیلی خوشحالم که شما هم میتونید این جلسه مهم رو دنبال بکنید و امیدوارم که تا آخرش لذت ببرید از این جلسه. All right, let's go to the contents of the thesis. Yeah, here I begin with the agenda of today. As you see, I started with my layman's presentation, and it will take around 15 minutes. After the layman's presentation, we will have a break of around 10 minutes, and then the committee will come from the other side of the room, and they will sit here, and I will officially defend my PhD defense at 10 o'clock. It will take exactly 60 minutes, and by the end of this official defense, we will have another break for around 10 to 15 minutes. There, the committee members will go to another room for the further evaluations and deliberations about the thesis. And around a quarter after 11 will be the degree award, of course, if I succeed to convince the committee members by their questions. And around 11:45 minutes, we will have a reception here in this building. All right, here you see the outline of the thesis. As you see, the thesis is written in 6 chapters, and I also follow the presentation here according to the format and the layouts of the thesis. You can pick up the thesis from here, an exemplary, the print version, but of course you can download it from the website of the TU Delft repository. And also for this presentation, for your convenience, I added a left blue bar where you can see where we are in the presentation. Let's begin with the introduction. Rolling contact fatigue in wheels and rails are a very important and major degradation mode of wheels and rails in the last couple of years has been declared by a lot of researchers. Squat and head checks are 2 main types of RCF defects. And squats, more interestingly, occur on the running band of the rail surface, and they appear with dark depressions or plastic deformation on the rail surface, which you can see also with this photo on the right side. You see the squat. RCF cause high maintenance and remedial costs for railways and the infrastructure managers. That's why it's so important for us to investigate it. Head checks are better known according to the current literature, and their initiation mechanism and preventive and remedial methods are better understood. This tells us this is confirmed by many researchers. But the study of squats had up to now less progress, especially their initiation mechanism is quite difficult to interpret. It has been a very complex and controversial phenomenon which involves a wide range of scientific problems, for example, fatigue behavior, vehicle track dynamic interaction, impact loading, thermal issues, and material phase transformation. I will get back to these terms later on in the presentation. The main goal of this thesis has been developing advanced methods for modeling, characterization, and testing of wheel rail contact in order to determine the degradation sources for the squats. Here we go directly to chapter 2, which is thermomechanical analysis of the wheel rail contact. We developed a new thermomechanical calculation tool in order to study rolling contact fatigue with much more focus on squats. The friction between wheels and rails is an important agent which provides adhesion and traction braking possibilities for the trains who are passing by. The mechanical energy is dissipated by the frictional work, and at the same time heat will be created in between the wheel and rail, so in the contact interface. The heating of wheel and rail components may be critical issue, as it may lead to thermomechanical fatigue or microstructural changes. I will get back to these terms later on. Here you see the computer simulation that I use for the modeling purpose. You see a piece of railway track with the wheel running on it. The frictional heat is generated during the wheel rolling on rail, and the thermomechanical coupling helps us to understand the realistic nature of the stresses that happen during this process, and of course to get the amount of flash temperature, the temperature exactly on the surface, which can be predicted from the modeling. Here you see some exemplary results for the temperature distributions and stress strains for different material models and different operational parameters, and you see how the temperature can rise up to 700 degrees for some specific rolling contact conditions. So we go to the conclusions. The main conclusions of chapter 2 are, in fact, the temperature rise and the thermomechanical stresses that we were able to calculate. And we understood that the thermal effect can cause material to fail quicker due to ratcheting behavior, due to fatigue initiation in the wheel rail contact mechanism. We also find out that there plays an important synchronization effect in the material damage, which means lower yielding limit at the same time higher stresses, which cause earlier damage to happen in materials. In some critical cases, we saw that the temperature could exceed the temperature which is needed to austenite to form on the rail surface. We call it the white etching layer formation. So the term has been used for white etching layer, which has a martensitic nature, and it is very prone to fatigue initiation. Of course, there has been many researches ongoing on this topic, and people in the literature believe that white etching layer is quite associated with the squat defects. Okay, let's go to the chapter 3, which is a test rig for wheel rail contact experiments. We developed a new test rig. That was the main goal of this research chapter, developing a new design and developing a new test rig suitable for studying wheel rail contact, and of course the main focus again on squats. When we began, we started the review of the available test rigs in the literature. We did a classification in between full scale and small scales. We compared their operational concept and their functionalities, and we also looked at their dynamic characteristics when we have wheel rail contact. The key features of the test rigs are nominated here. You see that we have used a proper scalability in order to have a scaled environment in the test phase. And the test rig is designed for the overall scale of 1/5, which has the flexibility of having a smaller or bigger wheel track elements. The real wheel rail conditions on real wheel rail materials can be included in the test. The main idea of this test rig is to apply and to include the high frequency vibrations generated due to impact loading, which are present in the reality. So we want to mimic them also in the test environment as well. And the rail circuit is relatively large in order to have the less amount of residual stresses due to the bending process of the rail. And here you see the final test rig, which is manufactured in the laboratory of civil engineering department here in this university. And as you see, that is a real the rotating frame structure having 4 wheel components, which will be operated on the track bed, which is a circular track bed, and it is capable of simulating wheel rail contact in the realistic situation. As you see, 4 multiple wheels can operate in order to generate fatigue faster than the reality. So in this case, we will have accelerated fatigue mechanism. It is quite important to have it in the laboratory environment. And the wheels can be reprofiled in order to avoid conformal contact or high wear in wheel rail materials. And the operational conditions, the traction behavior, and the constant speed are some examples that can be simulated simply by the test operation. All right, here you can see a number of exemplary results for the test rig development process and also for the measurements that we did with the test rig. You see the contact forces that have been measured and their magnitude and their frequency content. According to our simulations and our measurements, we found out that the results are comparable with the reality. We also compared the results of realistic case in order to see how close the results could be. And finally, we did a scalability analysis for a sample rail track with a scale of 1/5 to see how our scalability law will work and what would be the relationship between parameters of the test rig and how we can compare them with the reality. And here are some conclusions on this chapter. We did dynamic behavior analysis of the scaled vehicle track system, and we found out that it is quite similar and comparable with the reality. The design scaling strategy, which is used for the development process of this test rig, has been tested and confirmed that it is indeed a realistic scalability scalability concept. And we looked at the dynamic effects induced by the rail joint, and we saw that these are properly reflected and addressed in the test environment. So quite comparable with the reality. So that was also interesting to notice that after around 41,000 preliminary test revolutions, we were able to see potential corrugations in the test rig environment, which is quite interesting and also very unique in the current literature, that we have been able to produce such kind of defects, let's say potential defects in the lab environment. Okay, now let's look at the chapter 4, which is characterization of squats by CT scanning. And the main goal of this chapter was to develop a non-destructive detection and reconstruction method in order to look at RCF defects, and of course, with more focus on squats. When we have this technology, we can also use it to measure the size and also the angles of cracks that happens in the network of squat crack below the rail surface. We have some advantages for CT scan. We compared them with serial cutting, which is quite tedious and destructive, and we also have the idea of randomness when we do serial cutting. CT has also advantages compared to eddy current and ultrasonic technologies, which are somehow proven technologies in the railway engineering field. And we concluded that CT could bridge the gap in between the methods which can be used for macro crack analysis and the methods which can analyze the micro or nano cracks. Here you see the sample preparation stage that we've done during our investigations. Some samples are taken from the Dutch railway network in order to be further examined by CT scanning process. And a Phoenix nanotome high-resolution CT scanner has been used for our purpose. We examined the rail samples with the CT scan, and you see the general process of CT scanning here on the bottom left of this slide. So X-ray beams will be emitted to the object and will penetrate through the object, and finally we will get the results at the recorder. There is a computer next to the CT scanner where we can gather and we can analyze all the results that are obtained after each CT scan phase. And you also see the general process in order to do the post-processing of the results. And here you see some exemplary results for the CT scanning process. You see the 2D images and also how the 2D images are gathered in order to, are compiled in order to make and in order to reconstruct the 3D morphology of the cracks under the surface. So what you cannot see from under the rail surface is possible to be seen by the CT scanner. This is comparable with the medical application of CT scanner that you perhaps know from your personal experience. And here we have some conclusions on this chapter. As you see, CT could accurately reconstruct the RCF cracks below the rail surface. And we did the CT experiments based on CT experiments, and we compared them with the microstructural observations based on which we could confirm that this method is validated, can be validated through metallographical observations. The CT is shown to be a reliable technology for analyzing young squats. And the next conclusion, the quality of CT measurements on this and the CT settings have been investigated in order to create a kind of instruction for the future users who are going to use CT scan for this purpose. So they can use it as an, let's say, the recommendation in order to know what the samples should be and what the device settings would be. Chapter 5 is in fact the application of the former chapter in order to measure and in order to analyze the squat cracks in terms of geometry. The main goal has been establishing geometrical definitions, which has been missing in the literature because nobody up to now has looked at the cracks with such 3D mechanism and 3D reconstruction morphology. So as a first study in this field, we had to define the definition and also the main definitions and the convections for the general problem. We did non-destructive measurements on sample squat cracks, and we classified the orientations of the cracks, and we could determine the occurrence rates, their occurrence rates, and of course, we compared the results with the finite element modeling computer simulations in order to see how comparable the results could be in between the modeling and the CT scan, which are the real measurements. Here you see some definitions that we developed in this chapter in order to facilitate the characterization process. Here you see some exemplary results for the specific orientations that the crack under the rail surface might have. And you see here the angle ranges corresponding to each crack orientation, and we finally could classify and could categorize them, and also we found out what would be the order of crack initiation. So here are some conclusions on the last chapter, which are nominated here. We identified that there will be 4 crack orientations, and we calculated the amount of angle ranges associated with each orientation. And some orientations, we understood that these might gather and this might create V-shaped primary cracks for the initiation of the squats. And the results of finite elements modeling could prove that these are somehow related to the operational conditions of the train over the track. And here is a general summary of my research in total, and also a number of important points from the former slides. But of course, nothing will be more interesting than looking at these things in a video form. So let's look at this. As you see, the left one is the result of thermomechanical modeling. The middle one is the result of CT scanning. You see the red area, which is the crack under the rail surface, which has been transparented compared to the bulk steel in order to be able to see that. And the last one is the results of a preliminary test with the new test rig to see how it operates and how it works. Here are the list of publications which are also nominated at the end of this book, if you have it in your hand. And of course, the electronic version, as I said, can be downloaded from the TU Delft repository in the PDF format, freely available to everyone. And I would like also to add some additional words by the end of this layman's presentation. In a few minutes, the committee members will come from that door, and they will sit in here to examine my PhD dissertation. But before that, I would like to appreciate everyone who supported me on this long journey, especially my family, friends, colleagues, promoters, and collaborators. You can see on the left side of this slide, top left, a photo of my first day of working at the TU Delft. And at the bottom left, you see the final books that have been recently printed out of this long research. Of course, performing PhD research here in the TU Delft was the best chance of my life in order to improve myself, in order to learn, in order to do very deep research in the field that I'm really interested in, and of course to become the person who I am now. And by saying this, I will say that we will wait for the committee members, and I would hope that you will enjoy the rest of defense, especially the official part of defense. Thank you. Even there's an outset.
van het proefschrift en stellingen van Meysam Naeimi, Master of Science in Railway Track Engineering. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled An Investigation into the Formation of Squads in Rails, Modeling, Characterization and Testing. The Board for Doctorates of TU Delft has installed a committee to evaluate the thesis and propositions. The committee will have a debate with the candidate in public, and it's an honor to present the members for this committee, to whom I extend a hearty welcome. First of all, Professor Lee, University of Wollongong, Australia. Then Professor Fletcher, University of Sheffield, UK. Next, Professor Sietsma, Delft University of Technology. And Professor Nunes Vicencio, Delft University of Technology. Then, at my right-hand side, closest to the public, Professor Wolfert, Delft University of Technology. My right-hand side, Professor Dollevoet, promotor, Delft University of Technology. And at my left-hand side, Professor Lee, promotor, Delft University of Technology. Thank you all for taking part in this academic ceremony. My name is Witteveen, and I'm chairing this session on behalf of Director Magnificus. Now I would like to start the opposition and give the floor to Professor Lee. Please, Professor Lee. Professor Lee, could you start?
Yeah. It's my turn. I hope I can say it correctly. When the profundus. Now can I ask the first question? Yeah. So I've gone through EU thesis in a couple of times. I must say the EU thesis addresses a quite important problems, which is a squad or a real defect which industry, the global rail industry is currently facing. Here in Australia, we face the same problem. And I had previously, a couple of years ago, I had a discussion with Professor Lee and with also Professor Isma on this particular issue as well, the problem with real industry that is currently facing, and I think we know this problem for a long time, but at the moment I think we still cannot get the bottom of it, so I think overall your thesis and the contribution from your thesis is quite important and significant and to the real industry, and also has a quite good scientific significance. So if I may ask a couple of questions. The steel we're using for real industry at this stage predominantly steel political rail, which contains almost 100% pearlite. So we understand during the wheel contact and the temperature will rise or during at the surface of the rail, and so it may trigger the phase transformation during the service. So have you measured the phase transformation temperatures of your steel, say for example using dilatometer or other technologies?
By the promovendus, is this question clear to you?
Meneer Director, the question is clear.
Okay, please answer it.
All right. Hooggeleerde opponent, first, thank you for your compliment and also telling that you in Australia see more or less the same problems running on about the rolling contact fatigue and especially the topic of squats. As I understood, your question is whether we have the possibility of temperature rise, or what would be the amount of temperature rise which can induce the material phase transformation in paralytic rail steel. As you see in chapter 2, we have developed a new thermomechanical modeling by which we were able to calculate and to estimate the amount of temperature rise as a result of high sliding conditions, by which we could conclude that the amount of temperature needed, the amount of temperature in some cases would be above 700 degrees Celsius in very extreme situations, so that we can conclude that the temperature is higher than the limit by which we see the material phase transformation. I hope this answers your question.
Well, thank you very much. If I may, I'll continue. You did a fair bit of, look, in thesis, you spent per large chunk of your thesis on modeling work. So do you think the yield strength of real steel has strong influences on the outcome of the modeling? And how does this correspond to the steel grade, for example, plain carbon steel and high hardened rail? And also in modeling, what's your view on the work hardening or strength hardening at the surface of the rail?
Hooggeleerde opponent, as I understood, I would like to recall this question. Whether the yield stress would be important in the results of thermomechanical modeling in chapter 2, and as well the second question was if we have the for different type of steel materials, whether in physical conditions you might have different results or not. I would answer the first question by referring you to the parameters that I use in the modeling process. As you see, the amount of yield stress has been one of major important parameters that has been used in the modeling. And of course, we consider the more realistic conditions by considering the head hardened rail with having the amount of yield strength in the neighborhood of 800 megapascal, which is normally higher than the level that you see for the steel, which is recently comes out of the manufacturing process. And it has also been temperature dependent. So in this sense, we have considered more or less realistic conditions with respect to the yield stress. And the yield stress has been shown that would be quite important in order on the estimation of the maximum temperature which can be created by the rolling contact fatigue at high sliding conditions. I would refer to the results of chapter 2, by which you can see that as you have the higher amount of yield stress, your material goes to fatigue, goes to plastic region longer. So it takes longer time to go to the neighborhood of ratcheting behavior, and also in the neighborhood of failures due to fatigue initiation by ratcheting. So in that sense, the higher temperature would be, the higher yield stress would be more beneficial, because you have less chance of having ratcheting at early stage. But of course, you can also see that at other parts of the results that the high temperature can happen at higher level with the higher yield stress. So in this sense, if you have a very high chance of sliding, then a higher yield stress wouldn't be beneficial. And referring to your second question, we can say that if in a track that you have less chance of having high creepage or high amount of slip friction, then the higher steel grade will be more beneficial. But in case that you have a high creepage condition and you expect to have it in the operational conditions of the trains, then a lower steel grade would be better.
Yeah, thank you. Yeah, that's right. I think it's a situation dependent. It's dependent on the actual load of the trains as well. So let's talk about the white icing layer. So we all understand white icing layer potentially the precursor for squat and probably height checks during service. And we now also understand there's the both severe plastic deformation at the rail surface and the thermal excursion both can result in the formation of white etching layer. But the microstructures are different. So we know white etching layer caused by severe plastic deformation predominantly contains a nanocrystalline supersaturated iron carbon solid solution, whereas white etching layer caused by a thermal excursion contains a martensite and reasonably probably significant amount of returned austenite. So comparing these two kind of white etching layers, so in your view, which one do you think is more detrimental for the rail?
How clear the opponent? If I rephrase your questions, the first part would address if two types of white etching layer can happen and under which conditions, or perhaps which one has been the case in my research. The type which is called as thermally induced white etching layer, and the second one, the white etching layer as a result of very high plastic deformation, severe plastic deformation. And the second part would say which one would be more detrimental to the real situation, the operation of the vehicles on the track. I would say this is in principle the part of research which has been done by the material scientists in the framework of the same project by another PhD candidate who was working under the supervision of Professor Sietsma. He addressed that we have both types of white etching layer in the reality, according to the field observations that he has done on many samples taken from the sites. So it has been confirmed also from the literature that both types of white etching layer can be present. And in our case, the samples that we studied, he concluded, and also I referred in one of my papers, that the white etching layer is mostly as a result of high temperature, so induced by the thermal initiation, and also I would say the martensitic nature of the white etching layer has been the case. According to the examinations that these PhD candidates done, we could confirm that the microstructure of the rail is quite similar to the martensite. So therefore, he could conclude that the nature of the samples that have been studied in this research have been martensitic. And of course, I reported that in the literature, the second type could also be the case. But the problem is that we never know if in the reality, the white etching layer has been fade away, has been worn out during the rolling contact, normal rolling contact. So that is a bit controversial to confirm that whether you have samples that they may not have any reference of white etching layer on them. But having said that, there are many researchers that claim that this also could be the case. If we consider both types of white etching layers, and if we compare their microstructure to my own knowledge, to my own limited knowledge, I would say the white etching layer generated by the martensitic nature would be more detrimental, because the microstructure is more distinctive compared to the bulk steel. And as you said, the nanocrystalline morphology of the microstructure seen by the second type of well is considered to be more close to the pyrolytic structure. Therefore, there would be more chance of having cracks in the regions or in the neighboring regions around the white etching layer in reality. Therefore, I would consider well formed by martensitic nature more detrimental.
Okay, thank you. Look, you know,
my apologies, Professor Lee.
Yeah.
My apologies. Can I ask you a question? Are you satisfied with the answers provided by the candidate?
Yeah, Mr. Chairman, thank you very much. I'm happy with the answer. Thank you.
Thank you very much for your opposition. And I would like to continue the opposition by giving the floor to Professor Fletcher.
Thank you.
Okay, thank you. Vader Promen Fenders, thank you for sending your thesis. It's been a very interesting read. I've got some questions about a couple of areas. A lot of your simulation work was at quite really extreme conditions of kind of 10 to 20% or 10 to 26% slip at the rail wheel contact. And I was interested, for a railway with, say, mixed traffic, some freight, some passenger trains, how does that correspond to the real life, and what proportion of traffic would be exerting these type of conditions for the track?
Hooggeleerde opponent, thanks for giving this hint about the simulation results of Chapter 2. As you already mentioned, there has been extreme conditions considered with respect to the initial values in order to do the simulations. But in terms of creepage or the slip coefficient, I would say that it has been reported by some operators of the rail vehicles in the reality that they might have locally such extreme conditions. Of course, in order to get the result of temperature increase during the rolling contact, we have to study the very extreme conditions. And of course, you don't have squats everywhere. So in that sense, we may consider very extreme situations to also create very extreme defects, which are the severe squats. And this happens quite locally, according to my general knowledge. For example, at the insulated rail joint, for example, at irregularities, at the sharp locations of the irregularities, you might have very high or extreme slip that happens quite locally. And if it happens locally, you might also have the chance of temperature increase quite locally. And you also asked me what would be the proportion of such situations in with respect to the normal conditions in the reality. I personally didn't have investigations on these frequency examinations to see how frequent can be these extreme conditions happen, but I only reported the extreme cases that have been reported by the vehicle operators in terms of creepage in this case. So that would be also very interesting to investigate the possibility of having some results about the frequency and the proportion of such extreme situations with respect to the normal conditions. But it hasn't been studied in this research.
Okay, thank you. Thinking about your modeling of the wheel and the temperature rise of the wheel, in your work, I believe you've simulated a quarter revolution of the wheel and the temperature rise that took place during that, and you said you've captured the process in this. I was concerned about how the wheel, obviously the wheel is rotating and the same surface will come around again very soon. is a quarter revolution okay because you're modeling a very, very transient effect that could only last a quarter of a revolution? Or is it that you have worked out that that's enough even if multiple revolutions happen during the high slip event?
Oh, clear the opponent. Thanks for this question. I would recall your questions as whether the amount of wheel temperature would affect the results if it is hotter or not. This was the first part. Am I right?
I was concerned whether a quarter of a revolution is enough to capture the full physical process, or whether you've done something to kind of to assume something.
All right. So whether this short or limited distance would be enough in order to reach the stability conditions with respect to the results that you're gonna acquire from the modeling, and as well the second part, whether I have modeled the multiple wheel process in the simulations or not. I would address the first part of the question by telling some fact about the simulation, and that would be indeed interesting to have some clarification on this. You know, the transient dynamic simulations that had been applied in chapter 2 in order to do the thermomechanical analysis of the virial contact is based on two general problems. The first problem is the mechanical part, which is explicit integration method based on Lagrangian integration approach, which is considered to be less stable than the implicit integration method. The second point, the thermal analysis is considered based on implicit thermal integration method, which is in nature inherently quite stable, even at the very beginning time steps. So the problem lies more on the first part, which is the explicit time integration by Lagrangian method. There has been a wide amount of literature on the explicit simulations with respect to this method. There are a couple of tricks by which you can reach a stability in a quite shorter period. The first is to decrease the amount of time step as low as possible. If you have a very low time step, the difference in results by traveling from one time step to the next time step would be very small. Therefore, the waves that propagate through materials from the loading through the virial material will be quite limited in between different time steps. So, and also the temperature. For example, the temperature difference in between two sequential time steps would be less than 0.1 degree of Celsius, which is quite limited. This happens also for the stresses. Another trick would be for this is to satisfy with a specific stability condition which has been explained by the programming tool LS-Dyna, by which if you satisfy the amount of time step and also to satisfy the length and also the number of time steps where you can reach stable conditions. And also,
would those tricks be enough to capture that this heated region is going to go round and come through the contact again, and now it's already hot?
That's very controversial, I would say. It's not very simple to consider hot situation in the beginning. I would explain this as follows. Consider one wheel is rolling over a specific length of the rail. And consider very extreme situation, very locally happens, and the temperature rise at the contact patch increases as above 700 degrees of Celsius. After a few seconds, or less than 1 second, after a couple of milliseconds, but that high speed of the vehicle, the next wheel will come. So in this sense, you might not have the extreme situations again for the second wheel. So it would be a little bit, I would say, very super extreme conditions, I would say. The current situation is extreme enough, and in that sense, if you consider the wheel or the rail already hot for the second wheel or for the second cycle, it would be super extreme to consider the initial temperature higher than the room temperature. And I didn't consider this in the simulations due to this reason.
Thank you. I understand now, yes.
Professor Fletcher, can I ask you the same question as Professor Lee? Are you satisfied with the answers provided by the candidate?
Yes, I am. Thank you.
Thank you very much for your opposition, and I would like to continue with Professor Sietsma.
Thank you, meneer de voorzitter. Waarde promovendus, first of all, my congratulations on a very fine thesis, and also thank you for the collaboration that we had during the 4 years with the PRIME project. You mentioned the other PhD student already. It's been a good start, an interesting project, and a good start for our department to work together with civil engineering, railway engineering on a new line of research, which is being continued now with more PhD students. So thank you for that as well, for starting up this research line in our department, so the material side of railway steel. I have a number of questions to start with on the computed tomography technique that you use, so chapter 4 and chapter 5. First, a few practical questions. The wavelength, the wavelength spectrum that you use in the X-ray diffraction, is that a continuous spectrum, and what kind of wavelengths are they, and how are they chosen, and why? Can you elaborate a bit on that?
Hooggeleerde opponent, thanks for your compliment on the thesis and also saying these words about our collaborations with a group of material science at the TU Delft. As far as I understood, your question is what would be the wavelengths, or what would be the spectrum wavelengths of the CT scan
Yes.
process during the CT examinations. Let me think. You know, you have the sample in the CT cabinet, you have the sample in between the source of X-ray beams and also the detector. And then the X-ray beams will be scattered through the sample, will be penetrated, and at the other side of the cabinet, they will be gathered by the detector. I personally don't have any idea what would be the wavelengths of this radiation, but I have some information about the way that they have been detected by the sample, detected by the detector, and why you see some differences in the cracked regions, which lies on the difference in density. But I personally didn't capture or didn't read some information even from the technical catalog of the device. So I guess, and also my field of science is not physics, so I would say the radiation of photons through the sample is kind of a physics phenomenon, and I use it as application for my field of research. Of course, a physicist might have some idea about this, but I less.
I have some idea about it. I appreciate your honest answer. Partly the answer is in your thesis already, because there's a 180 kilovolt voltage applied, so 180 kilo electron volt will be the highest energy. And it's probably a continuous spectrum, but let's not go into too much detail there.
Thanks for answering the question.
Maybe one practical thing which you would have to decide, physicist or not, is the exposure time. When are you satisfied with a spectrum, with an observation? How do you determine the exposure time? And after exposure, you look at the results, and then you come to the conclusion that it was long enough or it was not long enough. What criteria did you use?
Hooggeleerde opponent, about the exposure time, it takes around a couple of hours in order to perform a CT scan on each sample. And so I would say half a day would be enough to complete the CT scan, but part of this time is also considered for gathering and storing the results on the CT computer next to the device. So I'm not sure if the total couple of hours, half a day, would be necessary in order to do the CT scan.
Why half a day? Why not 1 hour? Why not 5 days?
Could you please repeat this question?
Why do you choose for half a day? Why not 1 hour or 10 minutes or 5 days?
It depends on the power of the CT scanner. In the settings, you might choose a higher power, the higher power of X-ray images, and also the higher resolution, by which you might get a better resolutions of the images, which takes longer time. But in our cases, we have chosen the detectability of around 12 micrometer in each 2D images, by which it took us only a few hours, maximum half a day, in order to do for each sample. It also has to do with the size of the sample. If you have a bigger size sample and you define the situations in order to capture more details about the cracks there, you might need to do the examinations longer. And I would also like to add one more thing about the rotation, because the sample is rotated 360 degrees around the pivot axis, by which you can gather the results step by step, and you can detect the final morphology of the cracks at the detector site. And the steps for rotations, I guess it would be in the range of 0.1 degree at each step.
Well, then I would like to move on to the interpretation of the results, and maybe a nice typical example would be on page 67, figure 4.9. Figure C. Figure C is your observation, I think. And
yes.
Yeah, the top right figure C, is the observation, the direct observation, I guess, that the grayscale is the intensity. And then you move to figure F, in which you see the crack has become blue. So going from C to F, you have some criterion what to call a crack or what not to call a crack. You don't give any quantitative information on that. Can you elaborate a bit on what choices made there, what kind of, you say in the text, if the intensity differs from the intensity of the bulk, but it differs is a bit ambiguous, of course. You also scatter and variations in the values. So what actually did you do there to define the crack?
Hooggeleerde the opponent. As far as I understood from these questions, you want to know what would be the general mechanism in order to detect which a part of the 2D images would be cracked and which part not. This has to do with the difference in the diffraction morphology of the 2D images. The steel material by itself has a very homogeneous microstructure. So if you see any dark area inside the steel, it might be either inclusion or crack. This is my general understanding. So with any dark area, in this case black area, you might have some estimations about the presence of crack. So this is a kind of rough estimation which has also used in other disciplines, for example, for concrete structure. But for a steel, as you consider a very homogeneous structure, would be enough to detect the cracks only by seeing whether it's dark or not. And of course,
that's also very qualitative. The most important point I would like to ask, let's go to that then. You detect a difference in density, and that means that the crack should be more or less open, right? If a crack is closed, you don't have a difference in density. So the crack should be a gap, actually. And how big must that gap be in order to call it a crack? Is that the detectability of 200 nanometers that you mentioned?
It has to do with the detectability of around 12 micrometer. And of course, if you consider higher detectability, then you don't see much difference in the results, for at least for the samples that I studied. I also had the results for higher detectability, but you don't see much differences. At this level of detectability, you are able to see the cracks only by dark regions. And of course, there are also a couple of techniques by the software package which has been developed in order to capture the internal defects, by which you can segment the cracks. It's called segmentation process. As far as I know, there are 5 segmentation methods where you can apply in order to detect the cracks. I personally do not have, let's say, much background information about them, but I compare them. For example, the results of a gradual segmentation, which is one of the techniques, has been reported mostly in the images. So you apply one by one to see what would be the effectiveness of the method. So it's not done by the user. So you don't have the possibility to pick one pixel and say, okay, this pixel is cracked, the other pixel not, because it is a huge amount of work in order to analyze every 2D images. So,
okay.
So that we have to, in this sense, we have to look at the program, look at the software, and also the 5 techniques, and then compare them. Which segmentation method give you a better overview of the cracks? Some of them are quite nonsense, where you see almost nothing as cracked. And of course, I tried to compare the results with the microstructural observations in order to see whether these cracks are correct or not.
Professor Maybe one final question on this.
My apologies. I have to ask you, are you satisfied with the answers provided by the candidate?
Yes, I am, meneer de voorzitter. Thank you very much.
Thank you very much for your position. And I would like to continue with Professor Nunes Vicencio.
Thank you, meneer voorzitter. Waarde promovendus, congratulations for the fantastic work. It was a pleasure to read the papers and your thesis, and also to collaborate with you on the topic of big data and maintenance. I have the first question is about a sentence you have in the thesis. You mentioned that your findings can be used to develop treatment strategies to avoid or delay squats. And my first impression was to try to find a relation with grinding, but then I ended up that, well, the connections are not really straightforward. So would you please pick some examples on how the findings of your thesis can feed treatment strategies and challenging gaps that you will have to face to apply those in practice?
Zeer geleerde opponent, thanks for your compliments, and also that was also very nice for me to have collaborations with you as a researcher who has more overview on the maintenance strategies that has to be applied in order to save our system against the problems and defects that might happen. Of course, this research is purely mechanical, so by which you understand the origination of some mechanism behind some defects, but the practical way would be to apply it in practice by looking at the strategies that the infra managers already take in order to do grinding, for example. I will start with grinding. Grinding has already been used for many years in order to remove the initial cracks initiated on the rail surface, and in order to increase the lifetime of the rails. And it has been up to now a proven technology, but there are many debates on the amount of grinding and also the intervals that you have to do with respect to the initial defects. Of course, this research gives you some hints, some ideas about the size of defects, for example, the size of initial defects, by which you can consider what would be an optimal size of grinding per interval in order to remove the initial defects. Some other aspects could be to look at what, for example, when a squat can happen and which places are prone to a squat initiation. For example, in chapter 2, we mentioned high sleep conditions, so by which we can consider we can tell something about the possibility of S-course formation and specific places. So in this way, in this sense, we can include the results, we can combine the results to tell about the maintenance strategies which are needed in order to survive and in order to create a better lifetime for our material. I hope this answers your question.
Yes, more than expected. Thank you. You mentioned in your thesis that the test rig was constructed together with colleagues from engineering design, manufacturing process, and colleagues from mechanics, mechatronics, control systems. So, but then also not just the construction, but also the operation of the test rig will require a multidisciplinary team, a multidisciplinary approach. And for instance, one of the goals of the test rig is to obtain a certain reproducibility of results. And that was one of the major goals that you mentioned. But however, the local control systems from the test rig itself, they require loops of control to tackle stochasticities that they originate from the test rig itself, and that over time, over the cycles, they will accumulate over time, making that two initial conditions that you think that they are very similar to each other might lead over the prediction horizon to deviate from each other. So my question is, how would you suggest to handle those stochasticities that are inherent from the test rig?
Zeer geleerde opponent, I would rephrase your questions as follows. The first part says how we can deal with stochasticity in the real measurements that can be done by the test rig. And I would answer this by telling a little bit more about the nature of the test rig. You know, at every frame cycle, you have one full rotation of the frame structure over the track ring bed, by which you can create repeatable loading conditions. At the next cycle, you might have more or less the same situation, so that the repeatability of the results might be the case in the real measurements. That's why, after a number of specific cases, you might be able to see defects on the track because you have the repeatable conditions. Of course, if you don't have repeatability in the test rig environment, you might not see defect in a systematic way. And we confirm the repeatability by measuring the results that we can acquire from the test rig. For example, the contact force. We often reported the results of contact force generated by the GUI interface, the graphical interface of the setup, in order to see whether the results are repeatable or not. And then by comparing the results in between different cycles, we can tell that you are able to generate fatigue by repeatable mechanism. About the stochasticity, I would say most of the time let's initiate with this overview. In the test rig, you have nominally some values corresponding to the initial parameters. For example, the radius of the ring, the track parameters, and the vehicle parameters. But of course, in reality, you have always some deviations compared to the nominal values. For example, if you go along the ring in the test rig, you might see a different geometric value. The geometry is somehow different. The rail cant, the angle of the rail on the surface, is not always the same. The wheel component is not equal in between the four. So such kind of variations are all stochastic. So brings a kind of a stochastic nature for the test rig, which is quite comparable with the reality. In the reality, you have it as well. You have the track. It is considered by design to have the same structure along the rail of the track. But in reality, you might have some deviations. So this creates some stochasticity on the subject.
Thank you very much. Meneer Director, I have a question about Proposition 2.
Waarde promovendus, please could you read proposition number 2?
Proposition number 2 says, the mechanical wheel-rail contact problem looks like Kung Fu and Taekwondo. The thermomechanical contact resembles wrestling.
Professor Nunes, could you raise a very short question about this proposition, and could the candidate behave accordingly?
Okay. So, but when squats are included, the peak temperatures are short duration, and I see them like kicks that you might do with Taekwondo. And when you consider smooth rails, the mechanical wheel-rail contact problem is like a wrestling between wheel and rail. So what I'm not reading correctly from your proposition?
Zeer geleerde opponents. That's not the main direction that I want to say by this proposition. I would like to say by this that, in fact, that was my purpose. I did it on purpose in order to find something quite feasible for the readers of the thesis to compare with their daily life. If you look at a match, wrestling match, for example, you see a high amount of friction in between the opponents, by which the body temperature of the opponents will be quite soon very high, and they will be tired. So the duration of the match is quite short. This is somehow comparable with the thermomechanical behavior of the wheel-rail contact. On the other hand, when you have you are watching Taekwondo or Kung Fu, I personally did Kung Fu for a couple of years in my youth period. The idea is to have the less amount of contact, but at the same time, a very powerful hits. Even if you have a very long period of contact, then the referee is allowed to stop you by fault. So it's kind of comparable with impact loading of the system.
Professor Nunes Vicencio, you are satisfied with the answers provided by the candidate?
I am very satisfied. Thank you.
Thank you very much for your opposition, and I would like to continue with Professor Wolfert.
Dank u wel, meneer de rector. Waarde promovendus. I would like to discuss with you, before I go to my final questions on design and maintenance, I would like to discuss with you the following hypothetical, I would say, experiment. Suppose that we have a complete perfect track without any initial imperfections like squats or head checks or whatever. Suppose we would have a train which is completely moving at constant velocity. Could you reflect a bit on what will happen with RCF in that, let's say, experiment?
Hooggeleerde opponent, I would rephrase these questions as follows. If you have very ideal situations in terms of track characteristics and vehicle components, what would be the, let's say, the mechanism for defect in the system? In ideal situations, you don't have the stochasticity, which has been raised by another committee member, but of course you still have the permanent situation. For example, I refer to the head checks, which have more or less the quasi-static nature, and they can happen without any stochasticity, and also they can happen without any impact loading conditions. In this sense, you might be able to look at the defects which are considered to be initiated by non-stochastic nature. Head checks is one of them. There are other examples could be where you have always wear rate on the rail surface. And it happens mostly due to a very high contact pressure in the contact patch of the wheel and rail. So in this sense, I would say there are still some defects, and there are some sort of fatigue mechanisms which can support the idea of having ideal situation.
Okay, I agree with your answer. So indeed, I'm also of the opinion that fatigue will arise. But what is the predominant physical parameter for that? And please take into account in your answer wave mechanics, wave radiation reaction, that type of things.
The main, I would say, the main origination of fatigue and wear, in the sense of having non-impact loading condition, is that you have a very high amount of pressure, which is above the yield stress of material. When you are above the yield limit, the yield strength of rail steel, you have plastic deformation. And by plastic deformation, you have gradually, you are gradually closing to the region where you might have cracks on the surface due to cyclic plastic deformation. And it happens quite normally in the normal case. You know, nowadays, the vehicle operators are always dreaming to have more loads. They're always dreaming to have heavier loads, heavier vehicles, to carry more load, and as well to carry more passengers. So in this sense, you are creating the situation by which you have the nature of fatigue almost always in the real situation.
Okay, could you shortly comment on the effect of longitudinal stiffness in this case? So what would be the effect of rather stiff longitudinal train ballast system?
Do you mean the stiffness of a specific part in the vehicle, or the longitudinal stiffness?
On the track system.
On the track system. I would say the longitudinal stiffness of the track system has to do more on the dynamic characteristics of the total track itself. You know, we here focus much more on the wheel rail components, and I couldn't find any direct way of connection in between the longitudinal stiffness of the track and the defects that might happen in the wheel rail interface. Of course, if you have lower longitudinal stiffness in the track itself, there are the other modes of modes of defects that can happen. For example, track buckling due to low longitudinal resistance, or problems with ballast, or problems with sleepers. But in this sense, they don't have directly effect on wheel rail contact.
Okay, I do not fully agree with your answer, and therefore I have a practical question in mind. And suppose we would compare two different, let's say, rail systems. One is fully embedded, and completely embedded, I mean, okay, over a long part of the track, and the other one is the traditional one, which is more or less on your picture behind you. What would be the effect on having embedded rail system on the origin of RCF?
The question is clear. I would answer this by referring to the literature, because I didn't personally investigate this. This is my speculation on this fact. The researchers have also been able to see defects, rolling contact fatigue defects, and as well the squats in embedded rail systems, for example, slab track situations. So even at high speed conditions with a slab track configuration of the track, there is still a chance of having squats on the rail surface. So in this sense, it cannot be directly connected to the type of the track structure. At least the current knowledge, the current science is not enough in order to get such direct conclusion. And I'm also not personally in favor of having such a quick conclusion on this without having a very long examinations by field tests and as well by the lab experiments in order to confirm this.
Okay. If I listen very carefully to your answer, there is of course not the 0-1 effect of on one system there is no RCF and on the other there is. However, there is an influence, I tend to understand from your answer. And therefore I would like to go on a bit further in the design direction, I would say. Do you have other type of system design, so not only from the rail contact viewpoint, but from the, let's say, train viewpoint and or from the rail viewpoint, any other kind of recommendations to design the rail train system in a better manner, to of course avoid or to minimize RCF?
My speculation on this would be that try to remove the origins of the rolling contact fatigue defects. In this case, I personally studied the temperature effect, and it has also been confirmed by many researchers in the literature that temperature might play important role on the initiation of squats, and this has to do with the vehicle itself. So if we can have some vehicles that are more effective in the sense of creating less creepage or less slip conditions on the track, it might be quite beneficial in order to reach a better situation. This is from the perspective of the vehicle.
May I conclude with a very last question regarding the temperature?
If it is a very small
A
question.
small question. Okay, so it's a kind of yes or no type of a question. So, and it's a kind of maybe strange question, but you know maybe that in several places in the Netherlands RCF is occurring, whereas in another place it's not occurring. Especially, for example, on the track from Harmelen, Woerden. This is a typical place where RCF is more occurring. Is that then due to the temperature? Question mark.
Partially, yes.
I'm satisfied, meneer. I'm satisfied, meneer.
Thank you very much for your position, and I would like to continue with the promoter, Professor Dollevoet.
Dank meneer de rector. Waarde promovendus, I think it's a nice work and also I like to implement it, and that's only my question for today. How to convince rolling stock owners to make the traction control less aggressive so we have less problems, you could say. Do you have any idea to convince them?
Hooggeachte promoter, as I understood from this question, how we can politically, I would say, convince the rolling stock managers and operators in order to create a better situation in terms of traction behavior, for example. That's, the answer is also kind of political. In this sense, we have to see the system in a whole, I would say, because from the asset management point of view, we have to look at all the relevant aspects and also all the relevant components of the system quite involved in the methodology in order to capture or in order to generate a better policy for the track maintenance behavior. If they are involved in right way and if they have a little, I would say, some benefits from this process, they will be also eager to be involved. And from the again, from the political point of view, I would say they have to be responsible for such kind of defects if they happen due to the traction problem. But of course, science plays an important role to judge on that.
Okay, thank you.
Thank you very much for your position, and I would like to give the floor to the promoter, Professor Lee.
Dank u, meneer Rector.
Oh, please, could you put your cap on in order to impress the candidate?
Dank u, meneer de rector. What promovendus, you mainly did 3 pieces of work for your thesis. That is thermomechanical modeling, the design, and also then later on the construction of the test rig, and the last is then the CT scan technique. And suppose you continue then with the research, and what would be then the most research you would continue with? I mean, the 3 pieces of work.
Hooggeachte promoter.
Thank you, Madam Bidon. I request the promovendus to take his seat again. The committee will withdraw for further deliberation in the committee room, and this session is adjourned.
Ja, vooral de vragen vanuit material science kant was een beetje moeilijk. En de achtergrond muziek is dergelijke. Dus het is een beetje moeilijk om zo'n vragen te benaderen. Soms ben je een beetje voorzichtig. Klopt dit, klopt dit. Dus de achtergrond weet je niet helemaal precies, maar je hebt wel.
Wat is nog een dictaat die vraag stelt eigenlijk vragen op die schrijver.
Ja, ja, klopt.
En maar ook eigenlijk moet hij plaatsen bij slappe bodem.
Oh ja, klopt.
Arme boeren. Ja, ik was even verrast dat het. Blijkbaar.
Ja, is beter. Ja. Ja. Yeah, that's all right. Ja, that's okay. Ja. Mag ik één kort vragen stellen? Ja, zeker wel. Het levenswijze volgens mij is niet opgenomen in het begin van de hele wereld, want ik zag eigenlijk precies hetzelfde. Oh ja, dat was de bedoeling om gewoon ja, van het begin te doen, maar ja. Ja, graag. Ja, is goed. Ja, zeker wel. Want we zien alleen dit scherm, dus volgens mij in het begin is niet opgenomen. Maar ja, als het zo is, ja. Maar tijdens de echte verdediging is wel opgenomen, dat snap ik, ja. Ja, ja dat hoorde ik. Ja, dat hoorde ik, ja. Ja, precies. Ja. Dat is mooi inderdaad, ja. We gaan het doen, ja.
En kun jij het goed kunnen zien?
Ja, ja. Dat weet je wel. Dus mij is er een vraag.
Je kan nu even vragen.
Ja, dat is goed te doen.
Je hebt toch tijd nu?
Ja. Oh ja, dit. Ja, dat is prima. Ga ik doen. Ja, tot zo. Even kijken.
microfoon is nog on.